So today's lecture we'll be talking about linear buckling and nonlinear buckling analysis. It's a very important type of analysis that needs to be performed. In a lot of applications, we're not only concerned about when the structure fails because the strength of the material has been exceeded, or because maybe you have a composite failure, different failure modes in a composite. But in addition to that, it's important for us to determine whether the structure is stable under the loads is subject to. For example, if I take a can of Coke that's empty, most likely if you stood on that can of Coke, what's going to happen to the can of Coke? It's going to crush. So that's an unstable failure mode. Has less to do with the fact that the material capability has been exceeded, the strength, but has more to do with the fact that the geometry, the modulus, and the section properties of the structure were not able to support the loads. That's what happened there. That's what became unstable, and it buckled. Okay, so today's lecture is about that. It tends to be very important in a lot of applications. Civil engineering, the columns have to be checked for buckling. In aircraft applications, you don't want a skin to buckle. For example, you have rocket structures that you don't want to buckle, right? And so because of that reason, we need to examine this, and this needs to be part of the evaluation when you go to industry. So before I continue here, I'm going to show you a YouTube video which I think is worth watching. Oh. Is there a way to copy? Just type it in. So what we're going to watch is a video that NASA put together on buckling of structures. I think it's worth watching. Sorry about that. And as it applies to launch vehicles.
The test article is a 27.5-foot diameter, 20-foot tall aluminum lithium orthogrid cylinder.
How to increase the volume?
Very similar to the types of cylinders that were flying on the Space Shuttle external tank. In fact, this test article is derived from some
We need to increase the volume here. Can you check how to increase the volume from the computer? Okay, so what we're going to be watching is what NASA is doing with their SLS system. They're trying to save weight, and they're trying to basically determine the best ways to predict buckling, because if we can predict buckling accurately, then perhaps you can save weight when you design the structure. So with that, we're going to show you a video here. Let's see if we can hear it now.
The test article is a 27.5-foot diameter, 20-foot tall aluminum lithium orthogrid cylinder, very similar to the types of cylinders that were flying on the Space Shuttle external tank. In fact, this test article is derived from some excess hardware from the Space Shuttle program. So it's configured very much like the future SLS core stage tank structures, so it's very relevant to what NASA is designing today. In this test, we're going to be trying to simulate a lot of the same types of loads that a launch vehicle would be subjected to during flight. That includes internal pressure associated with the fuel tanks, as well as flight loads that you would see, and that would include compression type forces and bending forces, similar to what would happen if you crushed a beverage can under your foot. The black and white polka dot pattern you see on the outside of the test article is used in a system called digital image correlation. And what that system does is we have a series of 22 cameras surrounding this test article, and it's monitoring during the test minute movements of these dots, and from that calculating the displacements of the test article. It's a really powerful type of technique that allows us to watch displacements of the test article during the test on the entire structure, because traditionally we would only get point measurements, a single gauge here, a single gauge there. For something this large, the digital image correlation system really gives us a lot of good information. The NESC, NASA's Engineering and Safety Center, is the primary sponsor and funder of this project. They saw very early on the need to update these design guidelines, and I came to them with a proposal to form this project, and so they've been the primary funder. The primary stakeholders would be people like SLS, as well as commercial crew, and then industry at large. We have a large following of industry partners that come to workshops, and we discuss a lot of the data and discuss their needs as an industry. So this project, I think, is going to have a large impact in the long term, not just NASA and SLS. Well, we had several visual cues of this thing buckling. We look at data to see that it's buckled. We have our digital image correlation data that's streaming real time for us that indicated, even before buckling was occurring, that the buckling was anticipated. But we can also view the test article outside of our control room window, and we have it positioned in such a way that we can see it buckling at the time. And so it was quite dramatic. We could see it buckle, we heard the bang.
The shell buckling test has been conducted at Marshall Space Flight Center because inside of our load test annex we've got one of the largest tensile test machines in the world. We've got a movable crosshead that weighs 3 million pounds and can react 30 million pounds of axial compression, making it perfect to do large-scale structural tests. It's an indoor facility, which makes it ideal for the video image correlation systems that we use to monitor real-time strain distributions during actual load events. The space launch system consists of 5 major components: the forward skirt, the liquid oxygen tank, the hydrogen tank, the inner tank, and the engine section. I'm going to be the lead test engineer for the forward skirt and the liquid oxygen tank. One of the biggest examples of how this directly affects the space launch system is we're learning on real hardware that's the same size as, for example, the forward skirt. A matter of fact, the shell buckling test article is the same diameter as the forward skirt, and it's a little bit taller. So we've got a real life test article that we're practicing on, we're learning, and we're helping provide good data to the NESC.
Lift off.
These are the things that the industry is doing to try to gain insight into how structures buckle. Because if we can gain confidence in the analytical tools that we have in our hands, then we can then use those tools to predict when buckling will happen, rather than relying on tests every single time, which I think you still need to do as part of your assessment, because you still need to check that your analyses are capable of predicting buckling accurately. So let's go first and discuss what we mean with buckling. Buckling is, in essence, structural failure due to excessive displacement. So you're losing structural stiffness, and that usually happens when you increase the load to a point where the deflections now suddenly change and you have lost stability of the part. The buckling process depends on the loads, depends on the geometry, it depends on many other factors like boundary conditions and things like that. Here are examples of where I grew up in Puerto Rico, actually. I grew up in Puerto Rico, so this was a tank. I was in this, surviving the hurricane in my house, 1998. And so one of the water tanks buckled because of the winds were so large. It actually collapsed that tank. Here's examples of launch vehicles that have experienced buckling. Here's a Jet Hawker shear buckle. You can see that in the wall of that aircraft. Here, for example, there was an aircraft that was being designed so that the fuel barrier webs did not buckle. And so they looked at the shear webs and they found that these were areas that needed to be examined carefully. And so when buckling happens, it can happen in a stable manner or unstable manner. So if I asked you to provide me with a ruler, I think I can demonstrate with you that when I increase the load on the ruler, it will buckle first, sure, but then as I load it up, it's fairly stable in the sense I can keep applying load and the deflection will continue to increase in size, but I can increase the load and it's fairly stable. There are other scenarios, like if you took an arch, like shown here. If I took an arch that has a shape to begin with and I apply a downward load to that arch, that's going to look really unstable. So it's going to start about this shape and then suddenly it's going to buckle the other way, as you can see here. And as it transverses from this shape to this shape, it's going to have to change shapes and things like that. But this particular buckling behavior tends to be unstable. Here is a plot of deflection versus load, or load versus deflection. And usually load versus deflection, so say I'm tracking a deflection here where I apply that load. Typically this plot will give you a good sense of whether the buckling is stable or not. For example, as I increase the load, the deflection is increasing, and so here no buckling has happened. But as I increase the deflection further, now buckling occurs. And if it's under load control, you can see that it's going to snap to this point. So the deflections are going to increase dramatically from this point to that point for the same load. Well, that's clearly unstable. At the same time, when it encounters this load deflection curve, this portion, I can increase the load and that will be fairly stable at that point. If I were on the deflection control, so I'm applying the deflections myself and tracking the load instead, then I can now, for every deflection as I increase it, you can see here that I can calculate a load. But however, you can see the load is decreasing. So as I'm increasing the deflection, less load is needed to support that structure, right? So in that case, that's clearly unstable because with reducing the load, the deflections are becoming unbounded. They're becoming large. And so that's, buckling that's unstable. But once I reach this point here, you can see that both load and deflections increase in a stable way. So for example, I have this configuration. I can keep increasing the deflection here and the load, and it'll just increase in deflection, but it won't go unstable anymore. It's just basically in a stable state at that point. A lot of our structures are under load control, so when you apply a load, the structure will go unstable in a lot of our cases. Let's look at a column under compression loading. In this case, on the compression loading, you will expect that for a perfect, if everything was perfect, there's no imperfections, everything's straight, and I loaded it up, you expect that the load will increase, but the deflection will not increase. It will not increase. But at some point, you'll have a theoretical buckling load, a value at which you will expect buckling. For example, if I took a ruler that anyone will borrow me, if you have one, I could apply a load. Let's take the flexible one because the other one I don't think I can bend. But I can apply a load to that or a deflection to that. And for longest time, there won't be any outward deflection. It will be all straight for a long time if everything was perfect. And theoretically, there's a point at which this structure should buckle. Okay? And that is that point right there. Okay? But if everything started imperfect, say everything was, the initial geometry was about this. This is how the initial geometry was. So slightly imperfect, like every structure is. And I apply the load now, you'll expect the deflection to increase slowly with load. And you can see that here. As I increase, so these are for imperfect columns. So when I increase the load, the deflection slightly increases. And then there's a point at which, again, if I start with imperfect and I keep applying load, there'll be a point at which everything will become unstable again. Okay, so buckling in general is classified as stable or unstable. Typically, the example of the ruler that we just saw here, that will be under load control. It will become unstable because now I have a situation that I have excessive load. So I can, even if I decrease the load beyond that point, the deflection increases. This is true for this particular structure that we're looking at. So if we go back to mechanics of materials, I did not derive the equations here, but you can derive them very simply by basic principles. And what you will get is a governing equation for a beam. Okay? And you can derive that by doing equilibrium equations. So a free body diagram of a bent beam. Okay? And so this term usually shows up when you include geometric nonlinearity. Remember that when I discussed strains in this course, we looked at strains were linear. But in order to get that term to show up, you have to now include nonlinear terms. And so therefore, to evaluate buckling properly, you will have to include nonlinear terms, nonlinear geometry. And so that will become evident as I discuss Abaqus, why we need nonlinear geometry later on. But you do need them because in reality, those are the terms needed to predict buckling adequately. So if you go back to mechanics of material, that was a geometric nonlinearity term that was included. Mechanics of materials, you can look it up. The boundary conditions for this problem, as you can see, is a clamped end on the left-hand side. So these two are 0 at this end. And at this other end, the right-hand side, there's no moments applied. You see that? So therefore, W double prime is 0. And the deflection at this end is 0. We're not applying a deflection. And so with this governing equation and with these boundary conditions, the general solution to this problem is given by the equation here at the bottom. And mu is given by P over EI, square root of that. So how many boundary conditions I have? 4. How many unknowns I have? 4. So they have 4 equations, 4 unknowns. And what I will expect now is an eigenvalue problem. So here is, if I were to determine the characteristic equation, I'll come up with a non-trivial characteristic equation that looks like this. And then I can calculate the critical load for this particular scenario, which is this equation right here. So what is incredible about this, and I want you to kind of understand how amazing this is. What we're saying here is if I took a ruler, like the one you gave me, and I clamped it on the left-hand side, and I had a roller on the right-hand side, and I applied a load, axial load, to that beam, that beam will buckle at this load, 20.16 EI L squared. Notice that there's no strength properties. It's just modulus of the material. It has the L, which is the length of the beam. It has I, which is the moment of inertia of the cross-section. With that information alone, mathematics somehow was able to tell us when that particular structure should buckle. And so I didn't have to go to the labs and run a test because mathematically, based on the length, based on the modulus, based on the cross-sectional properties of that geometry, we're finding that the critical load is 20.16 EI L squared. Not only that, mathematically, I know it's going to bend in this shape. Okay? And so it's quite amazing that without having to do an experiment, nature, by means of mathematics, can tell us when the structure will buckle. Okay? So that's quite significant. And in fact, if I were to perform a test to that ruler with these boundary conditions, with that length, with that E modulus, with the moment of inertia of the cross-section, I will get a critical load in the test environment that will be similar to this. It will not be exactly that, but it will be quite close to that. Okay? So it's one of the few areas in structures that buckling only depends on the geometry of material properties. Think about it. The other stuff, if I want to know when a structure fails, I need to know the strength of the material. I need to know how weak the material is so I can predict failure. But with buckling, we can see here is only depend on the geometry, boundary conditions, and the material. And with that alone, I can tell when the structure buckles. Again, buckling means that I have excessive deformation with increasing load. So with small amount of increasing load, now have excessive deformation. The structure cannot withstand the loads are applied, and so now I have a buckled structure. If I wanted to do this with finite elements, the same problem that you learned in mechanics of materials, we can do that. We have the governing equation. I can multiply this by V to form the residual function. I can now integrate by parts. I did not show you how to do that because you know how to do this. And what I've done, I've split the order differentiation on W here, and I've split the order differentiation here as well. Two of them go with V, and then here one of them go with V. And then I've just done the integration by parts here for you. This is a pin condition. You will see that all these terms will go away. The boundary terms will go away. You can see that because, for example, this term is pin. Is that correct? Pin. So at this boundary, at the left boundary, V is 0, and then V is 0 at x equals L, right? So V is 0 in both ends. It's pin for this example. Pin roller, right? And then this boundary condition, there's no moments applied in a pin roller condition. There's no moments applied. So therefore, that's 0. And then also is roller, so that's 0. We discussed it. And so therefore, what I get here is a weak form of this problem, the pin roller problem. What I can do now, I can use a weak form Galerkin and use the approximation functions. Here are the basis functions that correspond to the beam. We've discussed this previously. So now I'll use those basis functions as my shape functions. And the shape functions are given by this. These are the unknown quantities at the nodes for a single element. And so what I'm trying to do right now is to formulate the element formulation, what we call it. And again, these shape functions satisfy the important properties of partition unity. They satisfy the Kronecker delta property, and they're complete, and they're called the Hermitian interpolation functions. I'll use this approximation function, W tilde equals M bold D, to now solve for the critical buckling load. That's my goal, using finite elements. So what I need to do, this is my weak form, this is my approximation function. Everybody agrees? Yes? And D bold is the nodal unknowns. And so now I'll switch V with N bold transpose. When I substitute this in here, what I get is this expression here. And you will see here that D bold factors out completely. And P is not a function of the integral 0 to L because it has a load applied. So now these are the integrals that need to be calculated. Okay? This is, in fact, the eigenvalue problem. And the unknown here becomes the load P. Okay? All these shape functions are known. EI is known for the cross-section. So all these integrals can be calculated. And when you do that, you get this stiffness matrix, which is the same one I discussed before. You have this new stiffness matrix. There's a problem with my equation. I don't know what happened. Can you take a note? So what should have happened here in this equation, we should have had this being evaluated. Okay, so when you integrate n transpose prime times n transpose prime times n transpose bold. So multiplying these things together, integrating them, will give me this matrix right here. And so what is a trivial solution? What is a trivial solution here that you see? So for me to have the left-hand side to be equal to the right-hand side, which is a column of zeros, then these have to be zeros. So there is a solution to the problem. The solution to the problem is that if I take a ruler that's pin-pin, or a bar that's pin-pin, and I apply, pin roller, because I want to be apply load, I want to be able to apply load, and I want to let it, shorten the deflection. So then, in that scenario, if I apply a load, the trivial solution is that bar stays straight. Nothing happens to it. Do you agree? Right? But there is a non-trivial solution. That non-trivial solution can be found by determining the roots of this characteristic equation. Okay? We're not doing that yet. This is an element formulation. This is an element formulation for single element, and it's true for every single element. So now say I take that pin-pin problem, and I want, pin roller problem, and I wanted to discretize that bar with 5 elements. What will you do now? So this is the element formulation. I have 5 elements. What do I do? I will use the element connectivity, and then I will now use this element formulation to assemble the system together. Then I'll apply the boundary conditions. Then I'll find the roots of the characteristic equations, which will be given by these buckling loads P. Okay. So for the example here, consider a pin-pin example, an axial compression load with one element discretization. So of course I didn't want to do 2 elements. We just did 1 element here in this example. So for single element, I know that it's pin-pin. So these are 0. In a pin-pin type solution, you're allowed to rotate on either the pin or the roller side. So those are free. And so if I cross out these 2, then I get a 2 by 2 stiffness matrix and a 2 by 2, we call this geometric stiffness matrix right here. And so when I calculate the roots of the equation, don't you agree there's a roots to this equation that we can find? We can find this by determining the determinant of that equation will give me the characteristic equations on P, on P. And so now, with 1 element, I get 9.69 EI divided by L squared. The second one I find is 74.31. Now, how many roots should I have in this example? 2, because there's 2 degrees of freedom. So if I had 20 elements, how many eigenvalues do you expect? I'll expect, but without, so I'll expect, so I have 2 unknowns per degree of, 2 unknowns per node. I have 41 nodes, right? So then I'll have 42. So let's start over. So we have 20 elements. How many nodes we have? 21. So how many degrees of freedom we will have if we don't put any boundary conditions? 42. 42 degrees of freedom. Now I apply the pin roller condition. How many degrees of freedom I have now? 40. So I expect 40 eigenvalues, 40 eigenvectors for that hypothetical example. In a continuous system, how many degrees of freedom do you have? Infinite. So you should have infinite degrees of freedom. The exact solution, in fact, is given by Pn equals n squared, pi squared multiplied by EI divided by L squared. If I look at the exact solution, the first eigenvalue is 9.86 compared to 9.69 from our solution. So not too bad. The second one does not match very well. I think that's expected. I only have one element, and I'm trying to capture the behavior of the second mode with one element. That's not possible. So therefore, we need to increase the number of elements, and as I increase the number of elements, I will approach the exact solution. Again, so here, the most critical buckling mode that needs to be used for design will be 9.86 EI L squared, because that's what we should be using. Any questions so far on how to apply finite elements for a single simple beam? Any questions on that? We could have used Timoshenko theory. We could have used some of the advanced theories discussed in this course. So just to make sure you understand, what we're saying here is that when I apply a load of this much for a modulus E for moment of inertia of the cross-section I, length L, that this bar, this beam, will buckle at that value. Okay? And so you'll have basically buckling of that beam at that value. In Abaqus, to do the problem, I gave you here the parameters you need. Type equals B23, that's your Euler-Bernoulli beam. Modulus 10 is 6, Poisson ratio 0.33. The first node I pinned it, the second node I have a roller. And then you make sure you put step definition and you have buckle. Star buckle will give you the eigenvalues and eigenvectors. It will give you that information. Linear buckling solution. I'm asking just for the first two eigenvalues. Then I have a pin condition, roller condition here, and then C load. Roller, I have the node set called roller, so it's basically node 2, okay? And then we're applying in the axial direction, so direction 1, I'm applying a -1, a value of -1. And so what Abaqus is going to do is going to find the eigenvalue. And that eigenvalue is going to represent the reference value, I call it reference value 1, times the eigenvalue. Okay? Those two together give you the buckling load. So for example, let's say that the buckling load is 1,000 pounds. Let's say that. So if I apply a value of 1, the eigenvalue I'll get from Abaqus is 1,000. If I put a value of 10 here, then the eigenvalue Abaqus will give me is 100. If I put 1,000 here, then Abaqus will say, well, the eigenvalue is 1. Now say I put 10,000, then it's going to use this 10,000, is going to multiply by the eigenvalue in Abaqus, which will be 0.1 in this case, to give you a factor 0.1 times 10,000 to give you a value of 1,000, because the buckling load is 1,000. So no matter what, the multiplication of the eigenvalue that Abaqus gives you times this reference value, those two together give you the buckling load for that beam. Is that clear? Yes?
Can you explain that again? So do we always define as the 1 or?
You can define it whatever you want to define it there. You can make up, give me a number. 10. Say it's 10. I put a reference value of 10. Then the eigenvalue you may get is 100 if the buckling load is 1,000. Okay? Is that clear? All right. So that is a load when this beam will buckle. Okay? Let's assume we put an imperfection to this structure. So let's start with imperfection, some small imperfection. So I start with that. If I put a small imperfection, and let's assume it's a sinusoidal imperfection, sine pi is x, I should have said xl. So I have an imperfection that goes along with that. With an applied load P, the governing equation is this. This should be doubly here, so I need some corrections. And so when I go here and I develop the equations for this problem, you will find that then if I divide everything by EI also, to kind of get rid of this EI, you will find that this is the governing equation for the problem, for the problem at hand. And previously we had this as 0. But now we have an imperfection, so we have this, this part of the equation coming up. Okay? And so if I solve this equation using mathematics or MATLAB, using the pin roller conditions, you will get that deflection is given by this equation here. Okay? It looks complicated, it's not, but that's the deflection you get. And so if I put it all in terms of load P again, because remember I made lambda P over EI, so I made lambda squared P over EI on purpose. When I go here, what I get is Vx equals this equation. PE is basically pi squared EI over L squared. Okay, so I just define it as that, which is actually the first buckling mode for this beam. It's actually the first buckling mode for this beam. So what is this telling us? As P approaches the value of PE, the buckling load, what's happening? Can you tell what's going on? It goes to infinite. So deflections are becoming unbounded, right? And so, but I can actually calculate a deflection. For any load, I can calculate deflection as long as it's less than the first critical value of PE, right? And so, you can see here, deflections become quite unbounded. They're proportional to delta naught, which is the amplitude of that initial imperfection. So the rotor, instead of being straight, is initially imperfect. Okay? So notice how I can actually calculate a solution. If the deflection was 0, there's no imperfection, what happens to Vx? It's 0. There is 0. So I'm not able to determine how this structure behaves as I'm applying a load. But in real life, you always have some amount of imperfection. And so my point here is that as I'm approaching that critical value, the deflections will become unbounded, okay, or will become very high. Anyway, so that's the point here, that imperfections will result in a solution that you can actually calculate. You can calculate the deflections of the real system for that imperfection that has been applied. Okay? Do you guys understand what I'm saying? So remember, previously when I calculated buckling loads, there's no imperfections. Okay? And the trivial solution was that the beam is straight. But there's a load at which the buckling will occur. You have instability, right? And so what we're saying here is once I introduce imperfection, now I can actually calculate the deflection. And that deflection becomes very large, linearly proportional to the imperfection amplitude that I start with. And then it increases significantly as the load approaches PE, which is the first buckling mode of this beam. Any questions on this?
If you're designing the buckling, then you just add in that initial deflection and then keep.
We'll discuss that coming up.
So we couldn't use the total potential energy to derive this?
We can do that. We can use the total potential energy, and we could have used weak form. Instead of using weak form, I could have used the total potential energy.
The information is done in color, can we use that?
We can use that, yeah. We can use the energy approach to solve this problem. I didn't do that here, but we could have done that. Same answer. Now, this is an analytical solution. We can use a weak form here, multiply this by a weight function, right? Integrate it, and we could just use weak form, right? I didn't do that. I want to show you the closed form solution to explain to you the effects of imperfection. Moving forward here, the linear buckling solution for shells. So if I have a cylindrical shell, which we'll be discussing today, and I were to calculate the buckling, the eigenvalues, the buckling, the mode shapes, we can do that using Abaqus. So I'm not going to go through a theory of that, but I'm going to show you the practical side of things. So you have a good understanding of that. But cylindrical shell is a little bit different from the bar example. The bar example, as you can see here, as I'm approaching PE, I'll get the beam to buckle. So there's no question about that. And that's not going to change. So the imperfection that I put into my system, you understand what I'm saying? So the imperfection I put into my system does not tell me, it's not going to change the answer when this beam is going to buckle. Because when P approaches P, you buckle it. So there's no question about that. With shells, it's a little bit different. With shells, I can calculate eigenvalue from Abaqus for a shell. Okay, so I can apply, say I take a cylinder, let's take a Coke, can of Coke, and I want to apply a load to the can of Coke that's empty. When I apply a load to can of Coke, to that can of Coke, there'll be a load at which that cylinder will buckle, but that's theoretically. We can calculate that with Abaqus. We can ask Abaqus, can you tell me when this cylinder, this can of Coke, will buckle? I can get that number, okay? And the buckling is going to look, it's probably going to look more like this one. I don't know. We can try if you have a can of Coke that's empty. You have one? It's empty?
I can make it empty.
Let's make it empty. Okay, can you stand here? You'll be, if you don't mind, let's see if you can buckle it. If you can, that's fine. We'll try a different can. That's too strong for us. Well, that was a dynamic problem. But we can safely say, you stood on that. You stood there. You stood on that can, and it did not buckle. So clearly, the buckling capability of that can is greater than your weight. But you did put a dynamic load into it, and you crush it. But assuming that the can was such that when you stood on it, you could buckle it, it'll probably look like one of this, okay? And so it turns out that when buckling happens, as you saw here, that's catastrophic. I mean, no question about that. I can't really do that to the ruler, right? I mean, you can try. Just show me. Can you make that, do that? I mean, you can try. It's going to take the first buckling mode. It's going to take that shape. Okay. Well, but it breaks, but it broke because the strength got exceeded, not because it's right. With a can of Coke, you can see here quickly how the structure became unstable, right? And so it has been found through a lot of experience from many people did experiments in the 60s to study. So they will have analytical solutions using very advanced theories, and they will find, well, the buckling solution I'm getting in theory does not match the experiments. They don't. And so here's your buckling solution, say for cylinder, simply supported, axially loaded, actually matches the hand calculation. So if you actually did the hand calculation for the first buckling mode and value for this cylinder, you'll match the analytical solution that Abaqus gives you, actually. But the question becomes, unlike the beam, for example, can the analytical solution compare well with experimental data? Will this solution that I get from here match what I will get from an experiment? And the answer is no. It's not going to match. And it's surprising to a lot of people because, it'll be nice if it matched, but it doesn't, okay? And the thing is that we can rarely get to this number. This, in the theoretical, this is the, for a perfect cylinder, this is what you will have gotten. But the problem is that, as you can see you see the mode shapes here? They tend to be shell modes. They're very localized. So let's take the ruler, for example. That first mode, it's not local. It's not like a little bump on the ruler, right? It's a first mode that's quite visible there, right? And so for a shell, though, the imperfections tend to be local to the wall. And so they tend to be small imperfections in the wall or small mode shapes in the wall. And so what happens is that if a structure is built and it has it has an imperfection. Say there's a very small imperfection in the wall. And I now loaded it up. Trust me, that imperfection will become very important. And so if I took that can that you had and I put an imperfection in on purpose and I loaded it up again, I'm pretty sure, well, you know, like if I took a can of Coke and put a dent in there, it would be easier to buckle than if everything was straight and there was no imperfection. Okay? And so it turns out that usually structures in general will have an imperfection. You may not be able to see it, but it's there. And so it turns out that this value here that you get from finite elements will not match the experiments because those shells will have some amount of imperfection. In real life, you will have them. And so here is a comparison of the experimental solution, the analytical solution compared to the experiments. And so if this is equal to 1, the analysis matches experiments. And you can see here that 1 will be when the analytical solution matches experiments for a different radius divided by thickness. So you can see that when the radius to thickness is fairly small, so let's take a radius that's small, the thickness of the tube is fairly thick. So in that scenario, we're maybe about here. In those scenarios, the analytical solution behaves very well, and that's because the mode shapes for those types of scenarios are such that the imperfections are not important. Okay? But when I increase the radius, like the SLS video that you saw, the radius was quite significant, and the thickness of the wall was very small. So in that scenario, you're probably about here, and so now your experiments divided by analysis, you can see here the scatter, right? The experiments are all over the place, and it's not matching what the analysis told us. And so for that reason, we need to now figure out why is that discrepancy. And that discrepancy, again, has to do with these imperfections in the shell. Okay? Imperfections in the shell. And so, and why the experiment vary that much? One could ask that question. Why is the imperfections, why is the experiments all over the place? Anybody knows? Because every shell will have different imperfections, maybe. Not one shell will have the same imperfection. And so for that reason, you will expect a discrepancy. Okay? So don't listen to anyone that says my analysis, my eigenvalue analysis for a shell is good. I can just use that value for a shell. For a beam, maybe, because I showed you that even for a beam with imperfection, the load, as the minute it approaches that eigenvalue is going to, that's basically your buckling load. But for a shell, as you can see, that is not the case. That every shell will be different. You'll have different manufacturing imperfections. Somebody may have dropped a tool. Maybe you have a dent. Maybe the shell is not perfectly circular. Maybe it's out of round. Right? So you can have various types of imperfections, and that's why you may have all these different predictions. Okay? Sorry, not predictions, experimental outcomes, which don't match the analytical solution. Okay. Here's another picture from another paper. This is taking radius divided by thickness. It has more data or different data from the other paper. This is a classical theory. Classical theory tells us that when I take the experiments divided by the analytical solution, that I should be at 1.0. And you can see here for different R over T's, that is not the case. I'm way off. In fact, I could be off. My analysis is saying I'm in here, and the test is saying, no, you're about 0.4, or maybe you're about here, right? It's significantly off, significantly off. Anybody has a question on what I'm explaining here? Again, the eigenvalue solution from Abaqus for a shell if I were to compare that to an experiment, I'll be off.
Why is it always higher than the
Because an analytical solution doesn't assume an imperfection. It assumes everything is perfect. It says you basically go to Abaqus, you model a perfect cylinder, and then you measure it and you run it. But in real life, that's not how it looks. There's an imperfection there. And on top of that, the Abaqus is looking at a linear perturbation about the perfect shape. In real life, you have a dent maybe in a structure or some amount of imperfection that you may not be able to see very clearly. And now the perturbation is not about the perfect shape, it's about that new shape, and that new shape will lead to unstable behavior. So for example, in the ruler case, these are fairly stable. Sorry for the ruler. It's probably dying little by little. Although it looks, I'm putting it here, and it looks fairly flat. So it's pretty good material. But we can see here, in this case, it's fairly stable as I load it up. In a shell, a small amount of imperfection is going to result in an unstable buckling behavior. While in this case, it's a more stable loading environment, right? Once I buckle this, I don't think I can put that back that quickly, right? So it just goes. And that's why it's very difficult to match experiments. Now, here's an example from 1981, a paper. They actually had a mandrel in the inside. So they had another thing in the inside. They actually applied pressure in compression. And with the mandrel in the inside, they were able to not get it to buckle catastrophically, because then the buckle just hit the mandrel and didn't let it buckle as much. But in those times, they were trying to study the buckling shapes. That you can see the buckling modes tend to be very local to the wall. They're not like the one for the ruler, which is just a big mode, one single mode. Another example is a test that was done in the 1980s as well. Or you can look at this reference, AAA Journal, Volume 19, Number 9, 1981. They have a great number of examples. That's where I got it from. I encourage you to go in there, get that paper. But again, this imperfection here, or this buckling shape here, is actually more of a global one in the wall as well. So this will be less sensitive to imperfections. I will presume so. But this is a stiffened, also this wall is stiffened, so it helps to prevent the buckling behavior. In that video you saw from NASA, it's an orthogrid. They showed you that, they talked about that. And those buckling shapes will be different from the ones you will see here, as an example. But stiffening the shell is one way to prevent buckling. It's one way. Not only thickening the wall can help increase in buckling capability, but adding stiffeners can help reduce the buckling, increase the buckling load, I meant. For torsion, so many people may think, well, when I apply torsion, I may not get buckling. So the example I showed you for the aircraft shows you those shear buckles. And so those shear buckles, in this example here, those are called that's caused by shearing, by torsion loading. Okay, and so torsion load, torsion will typically look like this. The buckling modes will look like wrinkles in the wall, and then here's a publication of NASA handbooks you can download for free. It's open to anyone that wants to look at them, and it has a closed form solutions for buckling of thin wall cylinders, thin wall truncated cones, double shells, and plates. So you can actually get the analytical solution, and you can compare them against finite elements. Not only that, you see this gamma here? Yeah? You see that gamma? Let's face it, it's a fudge factor. It's to get your analysis to match the experiments. So what people have done, they've done extensive amount of experiments, and since a linear buckling solution will never match the experiments, Why not just go ahead and use a database to then adjust the analytical solution, the linear buckling solution, adjust that, and get it to match the experiments? So that's one thing that people have done, and that's what these gammas do. They're called knockdown factors. Knockdown factors. So if you remember from the YouTube video, right, from the YouTube video, the gentleman, Mark Hilberger, was talking about the shell buckling knockdown factor project. You remember him talking about that? That's why. The NASA is trying to improve upon those factors that are published back then, and he spoke about that in the video. And they're doing that because the knockdown factors used today could be too severe compared to today's manufacturing processes. And so they also wanted to prove out that analytical methods can actually get you to predict buckling accurately. And that's what I'll show you today, how to do that. Again, the linear buckling solution didn't do a good job, but perhaps there's a way to use analysis in a way that's powerful, and I can now use analysis non-linearly in a way that I can study these imperfections. I don't have to run 200 tests, but perhaps I can run a large number of tests or reduced numbers of tests or no tests if you have high confidence in your models, right? Then you could do that, but you have to have very high confidence in those models. So what I'll be teaching you today is those techniques, how we can close the gap between linear buckling solution and experiments in a way that's practical and it has some meaning. Here is the knockdown factor that NASA SP 8007 has. So if you go in there, you will see this curve. And it tells you basically, if I calculate eigenvalue in Abaqus, lambda, I'll have to adjust lambda by a knockdown factor. So say the radius, I think the example today is a radius of, let's say it's 200 inches, and let's say the wall is about 0.1 inch. So what is R over T in that example? 100 divided by? Sorry? 1,000. So a radius of 100, thickness 0.1 inch, about 1,000. NASA SP 8007 is telling us we need to correct the analysis and multiply the eigenvalue I get from Abaqus, the buckling load. I have to correct that by a factor of 0.2. So I have to multiply by 0.2 and then divide that by the factor of safety minus 1. We'll do a few examples, or an example so you can see how to apply this. Okay? And that'll be my margin of safety for design. So today's example, we're going to look at, and Leonardo is going to guide us through that, so you can learn how to do it with the tools that we have. But we're going to look at an example of an axial cylinder, a cylinder subject to axial loading. And then one thing of note that I want to make is that in the example we're applying axial load, but we could apply axial load, torsion, bending, all the different loads at the same time. So we could have done that, but for the example problem, we're just applying axial load. And so what we're going to do is go into Abaqus and determine the eigenvalues that Abaqus will give us, and we'll see the eigenmodes as well. The input file, a few things to point out, although he'll go into more detail, is you'll have the shell section definition. You put the thickness in there. And then this is the element type S4R, a few things to point out. And then here is your start buckle procedure. In the start buckle procedure, you're basically extracting the first three eigenvalues, okay? And so this procedure here, you want to make sure you put start node fill U, because we're going to use this data later on. I'm going to explain to you how, okay? This is going to create a file that has these deflections, and that will be used later on in a subsequent analysis, okay? So now, does everybody agree that if I took a can of Coke, that when I apply load to that can of Coke, if it was empty, it would be easier to buckle than if it was pressurized? I think that makes sense, doesn't it? So you can account for that in this analysis, and perhaps we have time to do that today. Maybe we can apply a pressure this can or this cylinder, but you can quickly add another step before this step. So before this step, you can add another step, and that step you tell Abaqus, hey, pressurize this with a static load, so say 100 psi, 1000 psi, and then you go to the next step and get the buckling eigenvalue. So you can actually account for that pressurization helping the structure. We call this pressure stiffening. The pressure stiffening the wall is not allowing it to buckle. You agree that in that case that's the case? Yeah? Okay, so that makes sense, and let's think about that for a second. Why is that? So if you look at the wall, if I apply pressure, what's happening to that wall? Sorry? It's in tension. Yeah, PR over T and PR over 2T. So that wall is in tension. Now I apply compression loading. Isn't now that like counteracting the fact that I have pressure inside? So that's why you have this pressure stiffening effect, which is actually helping the structure not buckle as soon as if it had no pressure. And so that can be quickly included in this model, and it's not very hard to do. and perhaps we can, if we have time, we'll demonstrate that. If not, that's fine. We can talk about it after class, okay? So again, these are the important notes to pay attention. Start buckle is a procedure to get the linear buckling solution out, to get the eigenvalues, the eigenmodes, and then start node field will provide these deflections for these modes in a file, and that's what that's for. Everything else should be fairly similar. Okay, so continuing on, now I can write the margin of safety. So say the limit load in my application, so the load during flight conditions. During flight, the expected load during flight is 425,000 units of load. And I find the eigenvalue to be 1.147 million, which you're going to see that that's what we get through Abaqus. So then I take this 1.147 million. In our situation, I believe the radius is about 250. And I believe the thickness is about 2 millimeters. So 250 divided by 2 millimeters is 125. So when I go here, to this plot, I'm about here. That's about 0.54. So I take the eigenvalue that Abaqus gave me, knock it down by 0.54, divided by limit load times the factor of safety, gives me the margin of safety. That's negative. So I probably have to do some redesign work, potentially. Maybe increase the thickness, add stiffeners, do something to it. Okay? That's how we use this practically. Now, what if I don't want to use NASA SP 8007, or what if I don't have high confidence for my application? Maybe my application, NASA SP 8007, is actually not that good. It's supposed to be conservative. So NASA SP 8007 should be conservative. In this example, I chose it in such a manner so that NASA SP 8007 is not conservative. It's actually not very good. I did it on purpose. And what I want to show you is how to approach the problem in a different way. Okay? What if I now model the imperfections? I put the imperfections measured from maybe manufacturing, maybe through a laser scan, or I know imperfections that exist in my structure. And so I include that into my cylinder model. And now I run a nonlinear analysis. And this nonlinear analysis will tell me when the structure buckles. So instead of using an eigenvalue problem, what I'll do, for the ruler example, I'll start with an imperfection, and I'll load it up. And then I'll find when the structure buckles. And I'll show you what we can do to determine that, how we can do that with a nonlinear analysis. Okay? And so the nonlinear analysis is fairly straightforward. What you need to do is to run, so the input file looks like everything else you saw before. Nothing changes. The only thing that will change is that you will have a start imperfection before the step definition. And in this start imperfection, you're going to include the modes here. And you're going to select some modes. And what you're telling Abaqus at this point in time is take those modes, shapes, that have been actually normalized to 1. Because they're eigenmodes, don't you agree? Eigenmodes don't, amplitudes are arbitrary. But Abaqus will normalize them to 1. I think Nastran as well. Am I correct? It will normalize it to 1. And so I'll take the eigenmode, and what we're telling Abaqus to do, take that imperfection, take that mode shape, and use it as an imperfection to your model. And so what Abaqus is going to do is take the mode shape, move the nodes to this amplitude. In this case, 0.2 millimeters. It's going to combine, it's combining 3 different modes here. But I could just select 1 mode, 2 modes, 3 modes. My opinion, when it comes to buckling analysis, nonlinear buckling analysis, is to consider not just 1 mode, consider multiple modes, because you don't know what you will have in your situation, in your hardware, right? If you have the scan, if you know exactly what the imperfections are, if you know the thicknesses of the structure, you can use that information directly and move the nodes yourself. You know, take the cylinder model, write a code that moves these nodes in a way that includes that imperfection. You follow me? You follow what we're trying to do here? If I know there's a dent, somebody dented the cylinder, well, I could model that dent. I can make it dented on purpose and then run this analysis. The second thing we want to do is to make sure you have star step, but you have nonlinear geometry. Because when we're doing buckling analysis, we need to include the large deflection theory and large rotation. So you have to include NLGeom equals yes. And in here, we're going to show you a procedure called RIX. But you can also do just statics. But if you include RIX, it's going to actually enhance the solution procedure, and it's going to result in very nice converged solutions. It's going to actually converge very well using a technique called arc length method. We won't have time to discuss it here, but Abaqus has extensive amount of documentation about what this does. But in general, you can use this approach with no RIX in there activated, and it will still work very well. What we're doing here with RIX is trying to achieve a converged solution, because you can imagine if all right, do you agree that when we crush a can, it will kind of go, right? There's not much. So how do you get Abaqus to actually get that to work out, right? Because Abaqus will increase the load, and at some point the whole thing will collapse, right? But we want to slow down that process, so when it collapses in a way that's stable, although it's not stable, but we're trying to collapse in a way that's we call it static equilibrium. So theoretically, there's a state at which things can collapse in a way that's stable, static equilibrium. That is not going to happen in an experimental environment. But RIX allows you, using this arc length method, to be able to track the solution over load and deflection. Okay, it's able to do that. That's more for a more advanced course, of course, but I think I need to mention that so you're aware of it. Now, so we will apply a load of 1,000,000 and then let Abaqus run the analysis until failure happens. So in this scenario, Leonardo will show you, but when you apply a load, you can kind of walk through the steps, and you'll find that there's this one spot that gets hot, and that's the deflection. But you can also monitor other spots as well, where maybe the imperfections start to become worse at that point. So the mode shapes that we included, okay, happen to one of the imperfections from the mode shapes is going to make this region buckle maybe sooner than other places, right? And so what we're going to do is monitor this U deflection, the outward deflection, as a function of axial load. And then using that information, we're going to say, okay, it buckles. Now it buckles. Okay, so that's what we're going to use. I'll show you the steps.
Where do we get that modes?
Sorry?
Where do we get that modes?
So you get the mode shapes from the linear buckling solution. So that is from this step here. And Leonardo is going to show us in Abaqus how to do this. And then you're going to use these shapes. So now let's say, so what we're trying to do here, let me bring you back to what we're trying to do. I could have just used the mode shapes, use a handbook, and use a knockdown factor from the handbook, and just calculate my margin of safety. right? And the knockdown factor is a fudge factor to bring the analytical theoretical solution for buckling for shell in line with experiments in a way that's conservative. It's not always conservative. I will show you that today. You follow? But what we're saying now is, say I don't have a handbook for my particular situation. What can I do? What I can do now is run a nonlinear analysis and include the imperfection into my model. I could, and if I know the imperfection, even better, I can use the measurements from the hardware and put them into my model, run the analysis nonlinearly. That's one way. Another way is that I could include the imperfections created by these mode shapes. So the mode shapes have a preconceived shape, right? I'll use those shapes on purpose into my analysis, and I'm going to say, okay, my model has those imperfections. And it makes sense because you're more likely to buckle into one of those shapes. So if I use those shapes and I put an amplitude to that shape of what I expect in my manufacturing process, perhaps now when I do my nonlinear analysis, I'll get the buckling load that will in fact precipitate the buckling load, right? Because you need an imperfection to get it to go, right? And so we're trying to make that happen numerically instead of an experiment. And it's been proven that this works very well. There's hundreds of papers in this area. And the shell buckling knockdown factor project that NASA was talking about in the video is talking about that. It's talking about methods of improving those predictions. I'm just giving you some insight into that so you know how to do this when you go to real life experiences. So we're going to track deflection as I apply this 1 million pounds. And as I do that, you can see here, this is a max deflection as a function of, we call this load proportionality factor. So Leonardo will show us where to get this from. But as I increase the load, can you see here the deflection and the load proportionality factor is increasing linearly? So everything, basically that spot in the cylinder is moving outward at the same rate as we apply load. You agree? So nothing strange is happening. But suddenly, there's a load, about 40% of the million pounds, at which deflections go crazy. You agree? So the deflection went from 0.4 inch to, 0.4 millimeters, I believe. But this in millimeters, this model. And so 0.4 millimeters, and it went 1 millimeter and it's going to continue going unstable to maybe 2 millimeters. So we can call that buckling at that point, because isn't that the definition of buckling? The definition of buckling is you apply an axial load or you apply a load to a structure, and the structure with small amount of increasing loading, you have a huge amount of deflection that occurs. That's what buckling is. In your scenario for the can, you applied a load, although you did it dynamically, you put a really large force. The whole thing went, right? It just crushed. If you try that with a ruler, it's going to just break in half. Okay, but there you go. That's 40% is what we're getting of the 1 million pounds. And so now I can write my margin of safety is 0.42 times 1 million pounds. So I get 0.42 times 10 to the 6th. The limit load for my design for flat environments, I'm going to say is 425,000. Factor safety is 1.5. And my margin of safety is minus 0.34. Okay. Now, what is the buckling load compared from nonlinear analysis? This analysis that's more advanced compared to linear buckling load. So the buckling load I got with nonlinear, with imperfections included, is 0.42 times 10 to the 6th. What I got with the linear buckling was 1,147,000 times 0.54. So this is actually a larger buckling than what I'm getting with linear buckling compared to this nonlinear solution. This example shows that the margin of safety I got here, which is negative 0.34, is worse than the margin of safety I got with the linear buckling solution with a knockdown factor that came from a handbook. And you can see here that this is probably more realistic if that was our case, if we had an imperfection that had those amplitudes. And so not always a handbook is a good choice. Sometimes you may want to do this kind of analysis to study the sensitivity of the structure you're working on to buckling, to make sure it's not buckling, much earlier than what you thought. And so, all right. So, do you guys understand what we've just done? Yes? So let me summarize it really quick. You have a cylinder. So for a beam, if you do an experiment in the lab, you're going to match that pretty well. I think it's going to match. Not too bad when the buckling occurs. But when you go to a shell, because the mold shapes are typically local waviness in the wall, as seen also by some of the experiments we saw, the pictures, then any small imperfection can actually make the shell buckle. And it turns out the buckling for a shell is unstable. So therefore, when you get the linear buckling solution will not match the experiments. And so therefore, you have to correct the linear buckling solution to match the experiments using something called a knockdown factor for imperfections. And so since people have done a lot of experiments over time, then there's a database, and NASA SP 8007 is one of them. It gives you a knockdown factor that you can use for your problem. And so you use that, and you can write your margin of safety. The one issue, though, is that it may not always be conservative, number one. Number two, there could be situations that that handbook does not have for you. For example, you're looking at a problem that has a cylinder with a window. I don't know if there is a solution out there or an experiment out there that'll be representative of that. So therefore, you yourself are going to try to determine the buckling load for that scenario using a nonlinear analysis, using RICS, that uses imperfections from a linear buckling solution. So it's a two-step process. The first analysis is linear buckling analysis. The second analysis is a nonlinear RICS analysis, or nonlinear analysis. And in that nonlinear analysis, you're incorporating the imperfections that come from the mold shapes from the linear buckling run. You can read them in. Okay? So with that said, I'm going to have a demonstration. So let's take a couple of minutes break. So while we set up, is there any questions before we go to the demonstration?
Why do you call it linear compared to nonlinear? What is linear compared to nonlinear? You mean the approximation function, or what? When you're saying linear buckling?
So linear is using the strain displacement relationships, right?
Yes.
But is a linear analysis because we're doing it's a nonlinear strains. It's using nonlinear strains, but it's linearizing the equations, right? The stiffness equations, because they're nonlinear in nature for large deflections. You're linearizing that, and then you're finding the eigenvalues about the zero state, the perturbation state, which is zero state. Remember, when we go back to the beam problem, what is the trivial solution there? Zeros. So the linear buckling solution is about that zero state, right? The nonlinear analysis, in the other hand, is not linearizing the equations. It's using the full nonlinear geometry, the large strains, the large rotations. And now what we're trying to do is using the normal analysis that you will do, like a nonlinear analysis, determining when the structure collapses. Yeah? Another way to determine when buckling happens in a nonlinear analysis is to track the potential energy. The potential energy can also give you clues as to when the structure buckles. Okay? All right, with that said, take a couple of minute break and then be back. So
as Professor said earlier, we're going to try to model a shell, a can through a shell element, and we're applying some pressure in the second step. In the first step, the goal is obtain the mold shapes or eigenvalues that will lead to buckle structure. So that's the idea. So we're going to model. We're going to start by creating the part. So let's go to the part. we're going to select a 3D deformable shell through extrusion. Okay. So the first part is to create the cross section. The cross section will have a radius of 250 units. Yeah, 250 units. And we're going to extrude this cross section through 500 units. So here's the shell. Okay. The next step is to assign the material properties. So for this purpose, we could do only a linear elastic material properties. The Young's modulus for this material, which is aluminum. We're going to use a Young's modulus of 73,100, and the Poisson ratios of 0.35. Okay. The next step is to create a section. To create a section for this model is going to be a shell homogeneous. And the thickness we're going to use for the model is going to be 2 millimeters. Okay. Now let's assign the section to the entire model. The section is created. The next step is to create an instance. So we're going to make an independent instance for this case. Now, let's first set up the mesh for the model. So for the mesh, we're going to use a global size of 10. And we're going to use the sweep technique to mesh it. And the elements we're going to use for the mesh are going to be a standard linear S4 with reduced integration. So I think we are fine. So let's mesh the entire shell. Once the mesh is created, let's go to the step. So for this, in this case, we're going to select the procedure as a linear perturbation because we are expecting a linear response in our structure. Otherwise, if we weren't able to predict a linear, we couldn't use a linear perturbation. Okay, we should use general in that situation. And let's select buckle. For buckle, we're going to select only 3 eigenvalues for this model. By default, Abaqus uses vectors per iteration, 6 vectors per iteration. We can manipulate this number. There is a ratio that is 2 times the number of eigenvalues that you set up. Either 2 times the number of eigenvalues you set up, or the number of eigenvalues plus 8. Okay. So in this case, I'm going to stay with the number of vectors that Abaqus provides us. And the maximum number of iterations by default is 300, but I did several times this problem. So the more appropriate number is 1,000 to be safe. One more thing. The eigensolver for this problem is by default subspace. There is another eigensolver that is Lanzus, but Abaqus doesn't recommend it for simple problems like this. it will be, Langsos will be very helpful when you have more, like an assembly, more parts to proceed with this analysis. So subspace by default is fine, and the convergence will be guaranteed. Okay. So that's all we need to do. We don't need to modify any other parameter in this in this step. So that's the step we're going to use later. For now, let's apply the boundary conditions and let's apply the load to the structure. In order to do that, we're going to use a reference point. So if we go to the module interaction, we can select the reference point. The first reference point is going to be at the origin. So it's just 0, 0, 0. That's the first reference point. You can see it that is highlighted at the origin. The second reference point is going to be at the top of the shell. So the coordinates in this case would be 0, 0, to 500. Yeah, I think it's fine. The next step is to create a constraint. So it's a constraint that attach the nodes at the edge of the shell with the reference point. And to do that, we're going to go to create constraint. We're going to first create a constraint to the nodes at the top, at the edge on the top, as a rigid body type, because the idea is that the nodes at the edge will displace the same amount as that reference point. So the first instruction is to pick. Oh, thank you. Yeah. So the first step is we need to select the region type. We're going to use type. The next step is to select the point, which is a reference. So that point in this case is going to be the point number 2. And once we select the point, we're going to select the region that is attached to this point. So to select the region, we could select the nodes at this edge. That's one way to do it. But it's even better if we create a set before. Okay? Actually, that's the way I did it. So let me do the following. Okay, let's select nodes like this. All right, we are done in this moment. So just OK, and all the nodes in the edge will be follow the reference point number 2. We repeat the same procedure for the bottom. Rigid body, tie. We select the reference point, that is the reference point number 1, and then the area, the edge at the bottom, which is this. Okay. So once this is selected, we can move to apply the boundary conditions. So for the boundary conditions, at the bottom is completely constrained. So we're going to use encastrate this time. And what we're going to select is the reference point. So whatever, any boundary condition we apply at the reference point is going to be applied at the nodes associated with that reference point. So in this case, it's encastrate. And since we want to produce buckle, we're going to constrain that all the displacements for the nodes at the top, except for the displacement in the vertical direction. Okay? So in order to do that, we select the reference point. We constrain the displacements in the other directions. Okay, so that's done. The next step is to apply the load. To apply the load, we need to select the step number 1, which is associated with the linear perturbation. We're going to apply a concentrated force. The concentrated force is going to be applied at the top. So we select the reference point number 2, done. And basically, as Professor showed earlier, this is we're going to set this factor as 1, such that we don't need to multiply this number by the eigen value we're going to get in our results. So basically, this is just it's just minus 1 in this case. So now you can see all the boundary conditions applied, the load applied at this reference point. I think that we're done for this, for the first part of the analysis, which is with the goal of obtaining the mode shapes. So let's create a job. So this is the linear buckling. Linear buckling 2. So let's run it. Once we run it, just because we're running out of time, I did it earlier. So basically, this you could monitor. No, actually, in this point, you don't need to monitor anything because it's just one step, one increment. So we don't need to monitor. Just by running this analysis, the results that you were going to see in the deformed shapes are the following. So this is the first mode, right? And you can see the number, the eigenvalue at the bottom is 1.147, as you saw previously, right? The second mode is asymmetric respect to one of the planes. It looks like this, right? And the third mode would be this one. So those are the third modes. If I increase the number of modes, I will be able to see those bumps that you you saw in the presentation. But the problem is that it will require computation to run the nonlinear analysis. It would take too much computational expenses. So for this reason, I just work it out with 3 modes at this time. Okay? But you can do it by yourself. So once this is created, we need to go. We need to go to the input file. And in the input file, we need to add this this keyword, node field U, in order to store those eigenvalues that we obtain in this step, in the linear buckling step. Okay? Where do you need to do that? Just right before the end step. That's what you need to do. So start node field U, comma. That's all you need to do. Save it, because you will need this input file later when you perform the nonlinear analysis. Okay? All right. So let's get back to our model. We're going to use the same model to run the nonlinear case. The only modification we need to do is to get to the step get back to the step. We can suppress or just delete this step, because for the nonlinear we don't need it. We're going to use the input file. So let's delete this step. Okay, and let's create a new one. That's the nonlinear step for our analysis. To this step, we're going to use a static rigs. The static rigs, as Professor already described it, it's just a method that's commonly used to run problems when we have some instability, right? And we also have some general instability, and in our specific case for post-backlink analysis. So basically, this is the procedure we use. Since this analysis is a nonlinear, we're going to switch the nonlinear geometry on. That's the step you need to follow. So I want to call the attention for this. We have two sort of nonlinearities in the problem. We have the nonlinearity due to the geometry, which is this case, and we have the nonlinearity due to the material. So we could actually change our material properties and include plasticity if we wanted, okay? And if we don't do that, at least in the analysis I ran it, at some point the analysis is going to stop. So I did it in purpose, but the thing is, because I wanted to show you how is it, but it's going to take a long time to run it. And for the objective of this lecture, that is just show when the backlink starts or when the backlink happens. We're going to use just the nonlinearity in the geometry, and we're going to leave the nonlinearity in the material for another occasion. Okay, so that's all we need to do in this step, in this tab basic. Now we need to move to the incrementation, as we did it similar. We did it in the transient problems. We need to set the initial and the maximum. For the initial, we're going to work with 0.001 as the large length increment. That's the technique that Professor described earlier during the lecture. As a maximum step, we're going to set just one. We don't need to set up like this. Okay. And the number of increments, I'm going to set as 1,000. Okay. So that's all we need to set up in this step. This step, we don't need to modify anything. Just click OK, and the set is created. All right, so what is next? Once the step is created, we're going to modify the load applied. So this time, just in order to match what you saw in the presentation, we're going to create a load in the nonlinear backlink step, a concentrated force, which is applied at the top of the shell. And we're going to apply 1 million, okay? minus 1 million. 6. Yes, so that's the load we are going to apply to the shell. All right, so now we can start the procedure to run the problem. All the boundary conditions are the same. We are not modifying, and all the steps are the same. So we just go straight to the job. We create a job for the nonlinear analysis. for the nonlinear. We continue. Just click OK. And I'm going to show you now how you can monitor the progress in your analysis. So since I did it earlier, I'm going to call that file. That's this one. Yes. I'm going to show you how the monitor looks. Oh. Here it is. So here are the 1,000 steps I ran it, increments. Sorry, you can monitor each of them until you reach the increment you set up. You can see the errors coming up here, and warnings as well. All right. So this is the way. Now let's check the results. To check the results, we're going to select displacements, magnitude, and we're going to track when buckling starts to happen. So let me see. One moment. So this is what it's happening now. Something? Let's go. Okay. Yeah, it's better. So this is the first increment, second, third, and you can move on until the step number 29. And in that step is where you will see that the buckling starts to happen. Okay? So once you get there, you can plot the LPF factor, that is the load proportionality factor. That is nothing else but a ratio between the load applied and the load at the structure buckle without any load applied, right? So to do that, you just need to go to XY data, go to the ODB history output, continue, and select in this menu the load proportionality factor. Once you select it, it will show you the plot, the LPF versus the arc length. Okay? If you go to report and you select XY and you select the data that is in the viewport, you can extract that data in order to use it later to plot the curve displacement versus the LPF factor. Okay? So this is the way you obtain the data for the LPF versus arc length. Now let's see how we track the displacement at the critical node, which is we track the displacement of a node at the critical location with the buckle starts. So let's get back to the form configuration. All right. Again, go to the XY data, but this time we're going to use the ODB field output continue. We're going to select the displacement magnitude. We're going to select from the view one node, which is in that area. We're going to select this node. Once we do that, we can plot it. So this is the displacement versus the arc length. Excuse me? You remember that when we were setting up the nonlinear step, we set the incrementation time, and there was some arc length that could be defined. And the professor said earlier, it's a method that Abaqus used to follow, to track that backlink. So I think just to give you an idea, you can think about that like a time. It's like the displacement versus time. How the displacement is changing in time, something like that. Same thing applied to the LPF factor. It's how the load proportionality factor is changing in time. Okay, just it's how I see it. So same, you can follow the same procedure to extract the data. Once you extract the data for this plot, you can use it to come up with a plot displacement versus LPF. Okay, so this is the nonlinear backlink analysis, which is the set. Now let me get back to the input file. Before we run the analysis, we didn't create. This is something that we should do before run the nonlinear analysis, because we need to create an imperfection. All right. So before, once we create the job, and before we submit the job, we need to go to the input file that was written. When we go to the input file that was written, we need to link the first step, which is the linear analysis for the backlink, through the input file. So we need to set this line in the input file for the nonlinear analysis, which is a star imperfection. We need to call that file when we extract that information, which are the eigenvalues for the problem. And we need to set this 1 line, 2 lines, or 3 lines. Basically, what we're doing here through each of these lines is to modify those eigenvectors that we obtain in the first step. To give you an idea, it's those eigenvalues, those eigenvectors are basically the coordinate displacements in the x, y, and z direction, right? So by imposing this amount, let's say 0.2, we are adding that amount to each of those displacements. So it means that any of the components of the eigenvector will be modified, right? Based on those new eigenvectors, we're going to run the nonlinear analysis, because we are incorporating that imperfection. So since we modify those original eigenvectors, we expect that the result for the nonlinear analysis will be different from the previous one in the linear. Okay. Also, remember that we are applying some load, which is another difference what we did in the first step, I mean the linear analysis. So basically, this is the steps we need to follow to conduct the nonlinear procedure. Excuse me?
Yeah, for the different mode, you have a different factor.
Yes. The idea, what I did in this model was the first one, in the second one, I just changed half of the previous step. That's what I did. And the third one, I followed that track. But but there's no rule for that. It's the imperfection you want to incorporate in your model. Okay? Now, where I come up with this number, 0.2, 0.1, 0.05, that's coming from experimentation. It's like the sensibility of the structure, or in this case, of the shell, based on the experimentation. Measurements of manufacturing that leads to this number, to this factor. So this is.
If those measurements don't exist, then you do sensitivity study.
Okay. If those measurements doesn't exist, you need to follow one of the criteria, like a professor mentioned earlier, like the NICE criteria.
You use different imperfections.
Oops. All right. So yeah. So this is all the analysis. That's the implementation for the nonlinear backplane in Abaqus for this case. So thank you very much.